This lesson is for section 10.3. Today we're going to be talking about vectors. Our next couple lessons will be about vectors. Today we're going to take a geometric approach. We have three main objectives, so make sure that after this video you can accomplish all three of these goals here. But we want to draw a vector in the coordinate plane and be able to compute its magnitude in two different ways. So this is important, two different ways. We're also going to determine the resultant of two forces and find the horizontal and vertical components of a vector. If you can do these three things, then the homework for tonight should be pretty easy. So let's begin by talking about the very basics of vectors. Now, many physical quantities such as length, area, volume, or speed, those are represented by a single real number that we call scalar quantities. Now, other quantities like velocities and force, those require that you specify both a magnitude and a direction, and we call those vector quantities. So to help wrap your head around the idea of scalar versus vector quantities, I have a list of scalar quantities. So here's just a few, but we have 5 meters, 20 degrees Celsius, 256 bytes, 8,000 calories. Now, each of these is a different number that represents a different type of quantity, but it's just one real number that can describe that quantity. Now, when we deal with a vector, we're looking at not just in this particular example, a distance, but a direction as well. So 5 miles north, and this here is a speed 16 meters per second, but this has a direction west, which means this. Now, geometrically, a vector is a line segment to which a direction has been assigned. So here we see a line segment, and then indicating what direction it's going in is this arrow. So we represent that here with an arrow. It looks like a ray. Now, in the coordinate plane, a vector with an initial point O and a terminal point P is denoted by OP with a little ray above it. So it kind of looks like a geometry term for ray. It's also denoted by a boldface letter here, in this case V, or you can also denote that, in your homework, because it's really hard to show on your homework that you're using a boldface V. You can use a little ray above that. So it's either using the initial and its terminal point, or using just one single lowercase letter in boldface. So that's how you're going to see it in your textbook a lot of times. Now, there's a really important vocab term here, the magnitude of a vector. Now, the magnitude of the vector is simply the length of the actual line segment. So it'd be the length of OP. So we denote that with what looks like absolute value bars, but they're actually not absolute value bars. So a lot of times textbooks might even use double bars. In your homework, make sure you understand that you're finding a magnitude, okay, and that you're denoting it correctly. So you don't want to drop the bars if you're trying to show what the magnitude of something, of a vector. So vectors have both a magnitude and a direction, which is why they're different from scalar quantities. They have both. Now, we've talked already about what the magnitude of a vector is, and now we're going to talk a little bit more about the direction. So two vectors have the same direction if they are parallel and point in the same direction. So here, V and T are parallel to one another, so they have the same direction. Two vectors have opposite direction if they are parallel and point in opposite directions. Seems pretty easy, right? So we say that two vectors are actually equal if they have both the same magnitude or length and the same direction. So now we're going to come back to our notes for a second and expand on that whole idea of two vectors being equal. Now, in the first example, this first picture here, I have vectors A and B, and as you can see, they have the same magnitude, so it's the same length, and they are also pointing in the exact same direction. They're parallel to one another. So we can say that vector A is equal to B. Now, in the next example, although A and C have the same magnitude, the same length, they are clearly not facing in the same direction, so A does not equal B. Now, in the third example, both the direction is the same, but your magnitudes are not the same. So the length is clearly not the same for both A and D, so A is not equal to D. And finally here we have both the magnitude and the direction are not the same, which means A is clearly not equal to E. So there you have your vector basics. Now, I know that a lot of that vocabulary that we went over was review for those of you who've taken physics already, but not everybody in the class has taken physics quite yet. And I think it's really important too that you review those topics and that main ideas here so that you have a solid foundation now moving forward. So now we're going to try our first objective, which is to add two vectors. So there are two different methods that we're going to work with when adding vectors. Our first method is the head to tail rule. What this method relies on is the fact that two vectors are said to be equal if they share both the same magnitude and direction. So I can actually translate a vector and not change its magnitude or direction, and it would still be the equivalent vector. So I'm translating the vector to a more convenient spot. What that convenient spot is the head to tail rule here. So here we see the head of u and the tail end of v, or in other words, the initial point and the terminal points connected, okay? The resultant, this new vector here, u plus v, is called the resultant. So here you're actually seeing the sum of u and v. So this is if we were to add vector u and v, we end up with the vector u plus v. And that's, of course, the new vocabulary term here, resultant. Our second method follows the parallelogram rule. So our parallelogram rule states that the sum of two non-parallel vectors, u and v, is the diagonal of the parallelogram formed using u and v as adjacent sides. So we're still translating v, but we're going to put it in a different location. This time we used u and v here as two adjacent sides of a parallelogram. So we form a parallelogram here, and we draw the diagonal in of that parallelogram. That u plus v here is the same resultant that we got when we did the head to tail method. So let's try putting that into practice in a specific problem. We've got vectors pq and rs defined here with these coordinates. So I'm going to draw in the vector pq first. Now it's got an initial point, at 1, 2, and a terminal point at 2, 7. So make sure you understand the notation here, because this is your initial, this is your terminal. It's very important that we label that correctly. So here I have the vector PQ. Then I have the other vector here, RS, which has an initial point at 5, 5 and a terminal point at 10, 3. So we want to find the sum using the head to tail rule. So for that one, we're going to take this vector RS and we're going to translate that. We're going to take that tail end and we're going to translate it so that it touches the head of the other vector. So in this case, I need to move it up 2 units and left 3 units. So I'm going to move this end point here up 2 units and left 3 units. So now I have a brand new vector, which is the exact same, it's equal. So I'm still going to call it RS, but it's got a different initial and end point. So let me draw that in real quick. All right, so we just translated it. Okay, so this is the vector RS, and notice that it has the same direction and length. All right, now we're going to find the resultant, which is the vector formed by connecting this initial point here and the terminal point for your new vector. So this is the vector PQ plus RS. So it probably would be easier if we had labeled this maybe as, let's do this same as the slides I showed you. So this is u and this is v. So this would be the vector u plus v. Now we're asked to compute the magnitude here of this resultant. So let's compute the magnitude. Well, magnitude is the length of this vector. So simply finding the length here is just requiring us to use the distance formula. We're going to find the distance between points P and S. That's the resultant. So here we have the coordinates 1, 2, and 7, 5. So if I find the distance here, that's going to give me the magnitude of, let's do u plus v. So let's denote it with the bars here. So the magnitude of u plus v is going to be 1 minus 7 squared plus the quantity 2 minus 5 squared. So we have 36 plus 9, the square root of 45. Now we can reduce that, so make sure you're reducing your radicals here. That would be 3 root 15. Now for the parallelogram rule, we're going to start with the same two vectors. So I've got PQ and RS already drawn in. This time when I translate RS, that vector, I'm going to do it a little bit differently. I'm going to create a parallelogram. So I make these two vectors the adjacent sides of a parallelogram, which means I'm going to put the initial points together. So if I would want to put this initial point over here, I need to translate this down 3 units and then left 4 units. So I need to go down 3 units here and left 4 units, which will then place my terminal, actually let's do this in a different blue here. My terminal point is going to be a 6, 0. So I've got an initial point here and a terminal point at 6, 0. So as you can see, we're just translating that vector. It hasn't changed in either magnitude or direction. So this is the new vector RS. Now I create that parallelogram here, just translating those sides and just creating parallel lines there. And then I create the diagonal of this parallelogram. So here's the resultant. Okay, and again, if I use the same notation, let me get rid of this one. If I use the same notation as the last one, u and v here, this is going to represent u plus v. Now, if we are going to calculate the magnitude of u plus v here, I would use the endpoint p and the initial point p and the endpoint here. Let's call that, I guess, t. I don't know why I'm calling it t, but I am. So I want to take points p and t. That's the coordinate 1, 2 and the coordinate 7, 5. And lo and behold, it's the exact same coordinates. So I already know that u plus v, the magnitude here, let's denote it again with those bars, ends up being 3 root 15. So as you can see, if we use the head to tail rule or the parallelogram rule, we end up with the exact same resultant. Now our second objective is to find the resultant of two forces. We're going to start though with finding the resultant of two perpendicular forces because it's a little bit easier to understand. So here we have two forces F and G that act on an object. G acts horizontally to the right with a magnitude of 12 newtons. So this is a unit that we're going to use often that just represents a force. So let's draw that in first. So here's G acting horizontally to the right. So this is why it's a vector, because it's giving you that direction here. It's to the right. So this is force G, and that's 12 newtons is its magnitude. Now force F acts vertically. So here we're going upward with a magnitude, in this case, of 16 newtons. So this is F. Okay, we are supposed to find the resultant and find the magnitude and direction of this resultant force. So the fact that these are perpendicular to each other actually helps us out a lot when we create that parallelogram here. This one's probably going to be easier just to use the parallelogram method, because now this represents the resultant, F plus G. And if I want to find the direction and the magnitude, I'm going to use some right triangle stuff, because this is a right triangle. So if I want to find the direction, I need to find this angle measure here. I'm going to call that theta. And to find the actual magnitude, the length here of this particular vector, I need to use Pythagorean theorem, because I have the same length here. This is 16 newtons and 12 newtons, so I can use Pythagorean theorem to solve for the magnitude of this particular vector, F plus G. So let's do that real quick. Let's calculate the magnitude before we begin finding that angle measure. So using Pythagorean theorem, the magnitude of your resultant vector is going to be the square root of 12 squared plus 16 squared, which is going to give me the square root of 144 plus 256. So that's the square root of 400, which is 20. So that's the magnitude of your resultant vector. So now that we have the magnitude of that resultant, let's find the direction of our resultant. I want to solve for theta. So to solve for theta, I can set up a ratio. The tangent of theta is equal to 16 over 12, the opposite over the adjacent. And if I want to solve for theta, I would just take the inverse tangent of both sides. So let's use our calculator here, and we would put our calculator in degree mode. We should end up with theta is approximately 53.1 degrees. So here's our direction, and here's our magnitude of our resultant force. So I'm going to draw that in here. 20 newtons is our force at a direction of 53.1 degrees. So the calculations in this next example are going to be a little bit more difficult than the one that we were dealing with when we had two perpendicular forces. So here we're not necessarily dealing with perpendicular forces. We're going to find the resultant, and then we are going to determine its direction and magnitude, just as we did with the previous problem. So here it says that force F acts on an object horizontally to the right with a magnitude of 15 newtons. So this has a magnitude of 15 newtons. Force G acts on the object is indicated in the diagram. So here I have a 40-degree angle formed with that horizontal, and G has a magnitude, what is it, 5 newtons. All right, let's first find the resultant, and then we're going to calculate its magnitude and its direction. So we'll use the parallelogram method here because it's already kind of conveniently placed for me. We see two adjacent sides of what could be a parallelogram, so let's create that parallelogram. This is so beautiful. All right, now here's the resultant. It's the diagonal of that parallelogram. Let's calculate both the magnitude and the direction of this resultant. So that means I need to find this angle, and I need to solve for that segment here, this length. Now, because this is a parallelogram, you can use a very important fact about parallelograms. Remember that any two consecutive angles in a parallelogram are supplementary, so the fact that I have this 40-degree angle here means that over here I have a 140-degree angle. Now that's going to allow me to use the law of cosines in this particular problem because I can translate the fact that this was 5 newtons. The magnitude over here in this vector is also 5 newtons. So I have a triangle, and to solve for this missing segment, I would use the law of cosines. So the length of x, the magnitude of this particular resultant, is going to be the square root of 5 squared plus 15 squared minus 2 times the product of 5 and 15 times the cosine of 140 degrees. Now, after using a calculator, I end up with x being approximately 19.1 newtons. So that is the magnitude of your resultant. Now, to find the direction of our resultant, we need to calculate theta, and because I now have this particular side, 19.1, and you would want to store that value, now you can use the law of sines. So I'm missing this angle measure here, and I have a complete ratio, so the sine of 140 degrees over the length here of that particular resultant, 19.1, should equal the sine of theta over 5. So the sine of theta is going to equal 5 times the sine of 140 degrees over that 19.1. Please make sure that you've stored this in your calculator, or you have to type all of that back in. But if you don't, then you're going to end up with, a measure that's off by a certain, tenth or hundredth. So please make sure you're storing those values. So here we should end up with the inverse sine. If we take the inverse sine of both sides, we have theta as approximately, I wrote this down somewhere, 9.7 degrees. Okay. So there you have both the direction and the magnitude of your resultant. All right, the last part of our lesson is going to be our last objective as well, and that's to find the horizontal and vertical components of a given vector. Finding horizontal and vertical components are really helpful when we do bearing problems, so you really want to make sure that you understand this concept pretty well, otherwise you're toast. So anyhow, the vertical component of a particular vector is this segment here. So if we were to place a vector with an initial point at 0, 0, the segment that I draw in here represents the vertical component of that vector. Now the horizontal component of that vector is this distance here, which we denote as v sub x. So those are our definitions for the vertical and horizontal components of a vector. So let's now apply that to this particular velocity vector in the diagram below. So here I want to calculate both the vertical, this is the vertical, so this vertical component and this horizontal component. So this particular velocity vector has a speed of 70 centimeters per second and a direction of 30 degrees that's formed with that horizontal. Now I want to calculate the vertical and the horizontal components, okay? Now that vertical component is this segment's length here. So let's call that v sub y. So if I want to calculate this length, I realize that I have an angle measure already given to me, and I have this magnitude which represents just the length of that vector. So I can set up a ratio. The sine of 30 degrees should equal that vertical component over 70. So that's the ratio opposite over hypotenuse. So solving for my vertical component, I have 70 times the sine of 30 degrees. Since this is a value I already know, it's pretty easy to calculate. That's going to be 70 times 1/2. So my vertical component is 35, and that's centimeters per second. Now to calculate the horizontal component, this segment here, v sub x, I will take a different ratio. I have the adjacent and the hypotenuse, so that's the cosine. So the cosine of 30 degrees should equal v sub x over 70. And solving, I have v sub x is equal to 70 times the cosine of 30 degrees, again a value that we know. So we have 70 times the square root of 3 over 2, which is 35 root 3, and that's also centimeters per second. Alright, so that's the background for how you're going to set up and find those vertical and horizontal components, but I want you to find it a little bit faster than having to always set up these ratios. Okay. Now if you notice, your final, when you solve for your vertical and for your horizontal components here, we're seeing the magnitude of that vector multiplied by, in this case, the sine of your direction. So the magnitude times the cosine of my direction for that particular vector. This is going to save you time, so you don't have to always set up these, ratios to begin with. So I want you to be able to take the magnitude times for the vertical. Obviously, you're using sine. So basically, here, let me write it out to the side. So for your vertical component, you're going to take your magnitude multiplied by the sine of your direction. So if you remember, obviously, y goes with sine, you can just think of this as magnitude times direction. Okay, and then for your horizontal, again, it's magnitude times direction. In this case, it's with the cosine, though, since we're talking about an x value. All right, that is the end of the lesson. Nice job. I will see you guys in class tomorrow.